Welcome to the Engineering Room. We publish these conversations at the end of each month on the Continuous Delivery channel. So subscribe, and if you enjoy the content today, hit like and join the conversation in the chat below the video. The Engineering Room series is sponsored by Equal Experts, and I'd like to thank them for their ongoing support. So if you'd like some help building some great software or are interested in finding a great place to work, do check their links in the description below too. If you enjoy the content in general on the Continuous Delivery channel, you could think about supporting us as well. Go over to and think about joining our engineering community over at Patreon. My guest today is very well known. He's made a substantial contribution to our industry. He's a distinguished engineer at Google Cloud and works, amongst other things, on driving the adoption and development of cloud computing. He's a huge open source contributor and maintains multiple projects that help people to build and ship cloud native systems. He's probably most closely associated these days with his work on Kubernetes, where he essentially bootstrapped the adoption and technology and the community that formed around it. He's also seemingly very opinionated on lots of other topics too. Please welcome Kelsey Hightower.
Yo, happy to be here.
Thanks. Thanks very much for agreeing to do this, Kelsey. We don't know each other terribly well, but I've always been interested in the stuff that you talk about. I'd like to begin by just you painting a bit of a picture of how you got involved with Kubernetes.
Yeah, I would say, I entered the tech industry like many folks. I did tech support. I was a system administrator, eventually became a developer. And just working in industry in general, you kind of see all the problems with building software, shipping it to production, and keeping it running. And I spent time at places like Puppet Labs, working on configuration management tools. I've spent time in places like CoreOS in the early days of containerization, trying to figure out how to build the tools that are related to that stack. And so it was very natural when Kubernetes came out to want to contribute to this thing that seems to combine all the ideas from the previous parts of my career, and they gave it a name called Kubernetes. And so just contributing in the early days, making sure there's a concept of a node, some of the automation around it, cloud provider integrations. And of course, if you work on something, the next natural step is to talk about that work. And that's where the community involvement really came through.
Yeah, fantastic. So Kubernetes is one of those technologies that seems to be becoming increasingly pervasive. I've seen you talk in other places about this as kind of a standardized, it's a standardization move. We are standardizing the way in which we can deploy and manage more effectively distributed systems. Could you just describe that concept a little bit and why that matters so much?
Yeah, so like for the record, it's 2022. I probably spent very little time on Kubernetes in the last 2 to 3 years. And there's a reason why I can do that, because it doesn't change as much as it used to.
Yeah.
I think around 3 to 4 years ago, I think it kind of hit this sweet spot. And just like Linux, the operating system, right? The ABI for the Linux kernel is fairly stable. Whatever language you're writing in, more than likely, if it can target a wide range of Linux kernel versions, and it will probably just work for versions that are yet to come. Kubernetes is also in that sweet spot. And so when we think about what Kubernetes is, I was fortunate enough to be on one of the Kubernetes documentaries. And the Kubernetes documentary, they asked me about what Kubernetes is. And I went on to explain like the post office analogy of a person declaring where a letter should go, and then all the things behind the scenes that it take for that letter to get from point A to point B. But for a lot of people, when they think about Kubernetes, they're not really thinking about a scalable distributed system, bin packing, and all the scheduling algorithms that are built in. Most people are thinking about replacing their homegrown tools that take a collection of VMs and attempt to automate them in a way that they can just run their applications across them. So if you think about the fundamentals that people were exercising, the act of scheduling, picking the right node to run this application, if you look at it, what most people were doing is like keeping a spreadsheet, or they had some way of classifying that this node should be the web server. And then their scripts or configuration management tools like Puppet, Chef, and Ansible, they would then just carry out those actions on those servers. And of course, most people care about things like reliability. And so if one of the machines would go down, you wanted a mechanism to restore that machine and run those applications again. And of course, we tend to put these machines behind things like load balancers, right? We've been doing that for like 20 years. If you look at all of those fundamentals, Kubernetes just bakes those in. And so if you think about this from like the software perspective, you tend to have programming languages that start out with just syntax. And maybe that syntax is powerful enough for you to build your own TCP stack or even HTTP stack. But after you do that long enough, you want to have an HTTP library. If you're really fancy, you'll put that HTTP library in the standard library itself. And then over time, you realize it's just not deserializing headers and bodies. That's just not what you're doing all the time. You actually want an HTTP framework that can deal with things like routing, maybe rate limiting, and all the high-level things that it takes to actually run an HTTP service. Kubernetes aims at that much higher level. So sometimes it's good to think about Kubernetes as an infrastructure SDK or infrastructure framework, if you will.
Mm-hmm. I guess kind of generalizing that, what it's really doing is kind of raising the level of abstraction so that people can focus more on the goals of their software and leave more of the accidental complexity that surrounds it by it being distributed and running in the cloud to people like you.
Yeah, I mean, it's the same thing, a good HTTP framework does for you, right? You pick your programming language, Python, Ruby, Golang. The last thing you want to do is try to figure out like how to deal with the HTTP spec by reading the RFC. Like that gets very tedious. And so a lot of times you just want to use a nice web framework that has all these convenient functions and handlers for dealing with the various aspects of HTTP. And so Kubernetes does that for a lot of people. And it just comes from the practice of doing this for so long. Maybe we just have an opinionated framework to help you do it.
So one of the common drawbacks with frameworks is that they tend to impose constraints on the programming model, which is kind of reasonable because they need to exert some kinds of controls. In some ways, Kubernetes seems to have a relatively light touch to me, because basically you're just talking about manipulating containers. But in other ways, forgive me, but it seems to have a reputation as being a bit difficult to get to grips with. So
yeah, I mean, it would be a fair assessment. I think most people like me, when I go learn a new programming language, like if I go look at Rust, its memory management model, the way it thinks about expressing things that I know well in like 2 or 3 other languages, Rust seems overly complex to me.
Yeah.
I also attribute that to the fact that I don't know Rust. And so when you think about Kubernetes, a lot of people that come from the system administration world, the Linux OS and its userland is insanely complex. Yeah. Sed, awk, egrep versus normal grep, the GNU stack versus, right? It's complex. Terminals, the POSIX standard, these things are overly complex. Most people can't name the 100 plus system calls that the kernel implements. They just use the system calls that they need. And so a single server, single operating system, most people do not know the intricacies of how that work. But they SSH, they run things on it, they start things via init systems, and they get by with just enough of that operating system that they need. And if you think about what Kubernetes does, there's also a lot of nuance that goes into not just manipulating containers. Kubernetes says, listen, your app is going to make system calls. And so I'm not going to get into the details of Java versus Ruby versus Python. I'm going to force you to create effectively a tarball with your applications and all of your dependencies in it. And I'm going to take this chroot thing that you have in this container image, and I'm going to schedule it on one of those nodes, and I'm going to hand off that to the local runtime, run C or Docker. But that's an implementation detail for Kubernetes. Yeah. Now here's the hard part. Who should perform the health checks? And what should the health check API look like? Well, instead of making that from scratch, Kubernetes does say, look, your app probably needs a health check. My guess is your app probably also needs a mount point. It could be NFS. It could be some block store from the cloud provider. My guess is your app also has logs, and those logs should go to a central place. My guess is your app may crash from out of memory errors from time to time. maybe we should report those to some upstream system. What about that IP address? And once you get that IP address, should I register it into a load balancer? These are all the nuanced details that most people have never fully automated or scripted out. They end up cobbling together multiple tools, right? If you think about a world without Kubernetes, what are you doing? You have to probably use some init system. That init system, unless you're using something like systemd, may not have all the properties to express all your local dependencies on a server. What are you going to do for service discovery? Are you really going to scrape IP addresses from each individual machine and update DNS? Maybe you bring in something like console. And so I think the industry, if you really think about the amount of complexity that has always existed in this part of the stack, most companies have just gotten by building custom tools that nobody else understands and hoping for the best. And I guarantee you, if you look at those roadmaps, they have not implemented audit log, RBAC, namespaces, like all the things that it takes to have a proper system that you can actually share with other applications in a safe way. And so that total complexity, what Kubernetes does is just says, let's be honest about it. Let's encapsulate it in one system. And then let's give you an API to interact with all of that complexity. So if you're coming from system administration world where you only ever really acknowledged a fraction of that complexity, yeah, for the first time, having the full complexity landscape revealed to you can be daunting. But if you're new, I've met people who started their career just 2 or 3 years ago, and they've joined a team that only has Kubernetes. And someone says, I want you to deploy this application across multiple servers and ensure availability, service discovery built in, encryption, mounting volumes, and an API for collecting metrics. In their world, they're like, yeah, that's kubectl apply. One command. Mm-hmm. They get that by default.
Cool. So there's lots of dimensions to these. One of the things that seems to come out of that, I guess, is, as you say, it so much depends on your starting point. If you are coming into this new and you are kind of sheep dipped in the model from the start, then it's easy. That's the way that you're going to see the world. I'd say the same thing about things like test-driven development. If you learn to program with test-driven development, it seems natural and easy. And if you come at it later, it's harder work. So that makes absolute sense to me. But like an old crusty duffer like me who didn't come to it from there, one of the things that it seems to me is that there's often assumption in teams that I come across in my consultancy from time to time that it's the starting point for everything. And it seems to me that people are building, systems that are essentially almost single user, simple systems in Kubernetes because they think it's because Google told them to. Almost. I know that I'm doing you a disservice. I buy all of the things that you said. I think that raising the bar in the way that you said are really important. But are there what's the starting point? What's the nature of the project where Kubernetes is going to be, a win rather than an addition to the complexity of building the system? I hear of teams that seem to find it an addition to the complexity of getting started. And I don't know whether that's just because they're full of boring old farts like me, or whether it's because of some other reason.
Well, remember that the key here is use the tools you need.
Yeah.
I mean, you don't have to use TCP IP.
Yeah.
Right. You can literally say, I'm going to do this via UDP and handle all of the things that TCP gives you. You can totally do that right now. You can totally build an app completely.
I've done that lots of times.
Yeah. And so if you don't like TCP, there are some people who say TCP is too complex. It doesn't do a good job. Even HTTP3 is thinking about sidestepping it. Yeah. Okay. You can do that. No problem. If you have an app that can get by with a single VM, go ahead, do that. Yeah. That's like, what's the problem? Like, you can totally ignore everything about Kubernetes. Like when I go to Home Depot, I don't walk down the aisles of the more advanced tools and say, oh my God, why does this jackhammer exist? This hammer is all I need to hang pictures in my house. Yeah. Buy the hammer and totally ignore the jackhammer. Now, look, one day, someone in the world, remember, it's 8 billion people now, someone needs a jackhammer.
Yeah.
That person may not be you. It's okay. Like, I think a lot of technologists have this all or nothing thing, Vim versus Emacs, tab versus spaces. We can't help it. We can't understand why more tools exist in the world than I personally need. And then that creates this angst of like, do I need to learn this tool even though I don't need it? But also the thing we have to understand is we work on teams at larger companies that tend to have larger concerns than the ones that are in our own field of view.
Yeah.
And so, for example, if my company says we have a very simple app, yes, that monolith can run on a single server.
Yeah.
No problem. Then you don't have any issues. Just automate that process and be done with it. You got to keep the server patched. If the server were to go down or the zone goes down, I need you to build a tool that can reschedule that app to a different zone. You also need to update the load balancer. Hey, we also want metrics. And so you're like, man, that's a lot of stuff, because this is what your customer is asking. Forget what Google's talking about. Your customer assumes that you can have a globally available. I'm not saying every customer, but I'm saying a lot of people are just now used to this low latency experience from companies big and small. And so that single app on a single VM in a single zone ain't going to cut it in the competitive landscape. So what's your choice? You can definitely build all these things from scratch yourself. Great. But remember how we work as humans. We learn language from observation. Why do we speak English? I speak English because of where I was born. My parents speak English from where they were born. English is a very complex language. Like, we got duplicate words that mean the same thing, but not in certain contexts. It's overly complicated, but I use the words I need. So today, if someone gave you the challenge of running a highly available application, how would you do it? Would you start where everyone else is with this thing we call Kubernetes? Do you build something from scratch? So I think we got to make sure we look at the trajectory. Kubernetes is like 10 years old.
Yeah.
So lots of people are coming in from running their own Kubernetes cluster from scratch and dealing with all this complexity. I remember when people started with Linux, they used to build their Linux from scratch. They compile their own kernel, pick their own user land. And there was a big discussion around, should we even be using distros like Red Hat, Ubuntu, and Debian? Because they're so opinionated. They have their fancy package managers. I just want make install. Why do I need Git and RPM, right? Like this, but the thing is, the world is a big place. And once we kind of learn good patterns, just like software, when we learn how to do something, isn't on it for the language designers, the people who maintain standard libraries, to try to create a implementation that most people could reuse. So we're not having people recreate all of these things themselves. So that's what I would say to people. Kubernetes is complex. You may not need Kubernetes. This is why I work on Cloud Run. I work on serverless stuff at Google, right? And then attempt to replace Kubernetes. But the Kubernetes API has been so great for articulating the things you want. I have an app. It needs this much memory, this much CPU. It needs a volume. It needs to run in the zone. It needs the sidecar container because I'm delegating some of my app stack to Apache or Nginx. Okay, we still need to describe that. And maybe it's not Kubernetes that actually runs it. Maybe you give that description to Cloud Run where there is no Kubernetes to be found.
I like that way of describing things. I think that fits very nicely with my own philosophy of software development in terms of, the way that I try to express it. It seems to me that our job as professional software developers is to solve problems with software, not just to be good at the tools. So the tools are fantastic. It's important to have good tools, and using tools that allow us to worry about one part of the problem separated from another part of the problem, and make changes in one part of the system without another, and raise the bar on the level of abstraction so that we don't have to worry about some of the accidental complexity that's going on around us, is all vitally important to be able to move quickly and efficiently. But fundamentally, the job is to solve the problems. And I would pull that message out from the way that you talked about that, which I like a lot. which gets me onto another one of the ideas that I was thinking about before talking to you today was, one of the things that I think is interesting in terms of, the challenge of design is, how do you get to that kind of API that Kubernetes has that allows you to do what you've successfully achieved, which is to come up with a version of the software that you don't have to worry about anymore because it does it good enough. I'm putting words into your mouth, slightly overplaying what you said, but you nearly said that. So you've got this great API that's stable, that millions of people, presumably all around the world, are interacting with, and that's a hard thing to do. The model that I always have in the back of my head when I'm thinking about those big public APIs are operating systems. You get an operating system. You mentioned Linux. You get Linux out there. You've got a stable API that's been stable for years in some places, and you have an approach to being able to add new things and grow it in disciplined, careful ways. I'd like you to just talk. You are probably, you have personal experience of doing that, of designing those sorts of publicly available APIs that if you change, you're going to break hundreds of thousands of people's code. So how do you go about thinking about that and doing that and achieving it?
The same way we do this for programming languages. If you have a standard library, you have some contract with the ecosystem. Sometimes you even write it down. Here's our SLA. We will never break backwards compatibility. That could be your stance. Kubernetes has this stance. Once a API goes 1.0, we don't change it. And so this is why Kubernetes in its early days, we always had alpha, beta, and V1. We also have categories of APIs. So we have core APIs. These are the ones that we feel that the system must have in place to work. So like RBAC. The concept of a pod, which is a running instance of your application. Then you have things that are called apps. These would be things like deployment objects. And those actually came from Red Hat, right? Red Hat decided to build a PaaS on top of Kubernetes. So if you think about Kubernetes being this very low-level standard library of infrastructure design, then a PaaS like OpenShift would be an implementation that actually adds additional features to it. And they decided, and they found a good sweet spot of an API that said, what happens if you build an update mechanism into and writing an application? So we end up with the deployment objects. But we were really careful to make sure we understood what things were considered standard core library components that were composable into higher level constructs. But also we realized that unlike a lot of infrastructure systems that came before, Kubernetes also has an extensible framework that says, you can design your own API and do your own implementation. So while Kubernetes does ship out of the box things like jobs that you can run, cron jobs, a static web server, that's up to you. But you can also just define a new type, literally, right? It's called custom resource definition. And what that does is it takes pressure off the standard library that we don't need to implement everything on behalf of everyone else. Yeah. You can decide that you have a new API, you decided schema, you decide what promises you want to keep, you decide the version, and then you implement the implementation of that API using any programming language you want. And here's the trick. You don't even have to implement it using a container. You can totally just register your API inside of Kubernetes, and you automatically get watch semantics, or you can just poll the API for state changes, and you can implement it using a VM or a serverless function on Lambda if that's the way you want to implement that particular contract.
Cool. So I one of the reasons that I wanted to start down this path and talk to you about this was because this seems to be one of those ideas to me that is that teams or in other organizations that are not building those kinds of public APIs necessarily, but can learn a lot from, because what we're talking about here is API design, protocol design, designing things with good separation of concerns and nice abstract approaches where you can kind of hide the detail of what's going on and allow people to interact with it and take advantage of the services that you provide. So this you apply this kind of thinking on a small, I would say, I'm not trying to put words into your mouth, but I would say that you apply the same kind of thinking on a smaller scale when you're doing things like trying to create a platform in a platform team in an organization and so on. So that kind of design thinking, which I think we need more of in our industry,
Kubernetes was born
key.
that way. Kubernetes was born that way. I think a lot of people may not remember when Docker came out. Docker had an API basically to optimize doing things on a single system. And Docker tried to extend that API almost as is to represent managing apps across multiple systems. And honestly, that API just wasn't suitable. And so when Kubernetes came on the scene, we looked at that API and said, you know what, we need to design something different. And we started with use cases. An application is usually a logical thing. It requires more than one container to actually do its thing. But also we were thinking about, well, how would you articulate things like health checks? And so when we designed that schema, we asked ourselves, like, what does that look like? What things make sense to people? And so we would talk to people. We would actually run some analysis and say, how are people doing health checks today? What are the industry standards? And can the API capture those? Maybe not allowing people to do it only one way, but just high level enough. And then we actually started small every single time. We add a field, we observe its usage, and we propagate it all the way up to maybe beta, where we have one last opportunity to change or extend based on real world usage, and we have another go at it. But I think the KRM, the Kubernetes resource model, is probably one good example. One good example of seeing the infrastructure world realize we should be designing our infrastructure tools, not just scripting them.
Yes, yeah, absolutely. And that seems key to me in this move to be able to do what we've been talking about in terms of raise that level of abstraction. We're trying to hide detail, at all layers in our system. Very often, it seems to me. I wrote a book about my thoughts on what modern software engineering is like. It's about, and one of the key, I divide into two groups of principles. One of them is optimizing for learning, and the other one's optimizing to manage complexity. And that second group seems key to good design to me, which Kubernetes clearly is, in terms of being able to, apply what at least in the way that I think about it, ideas like modularity, cohesion, separation of concerns, abstraction, and coupling with a preference towards loose coupling, in order to be able to hide information in a way that allows you to make change anywhere in the system without breaking anywhere else in the system. And Kubernetes seems to be doing a fantastic job of being able to do that for some quite complicated things, but it takes that abstraction that I think that you're talking about is the way that I would think about it.
But I think one thing we're seeing, though, given the fact that there are so many people who are now classified as developers, meaning the world wants experiences, right? They don't care about low-level concrete and chemistry. They want a bridge that has bike lanes and that can actually move when a boat comes by. And so what we're finding now is that all the people that have been working on these abstractions and libraries and concepts, great, they're Lego bricks. That's it, they're Lego bricks. What people want from those Lego bricks is to build things. And so now when we think about, I would say design now is, if you have no user experience, more than likely your product or service will fail. It can be the best architected, most composable, most tested, and people will look at it and say, yeah, it's not usable by humans. The compiler's happy, the customer's mad.
Yeah.
And I think that's where I think now you're getting feedback from customers that use systems like Kubernetes. When they talk about complexity, is the fact that Kubernetes actually, by design, never really attempted to approach the user experience component. We always felt that should be done at a different layer, maybe some GUI, maybe something that wants to be a serverless platform could actually hide the low levels of Kubernetes. So I think what people are looking at when they look at Kubernetes, they're looking at the kernel syscall interface. Yeah. They're not looking at the bash shell. And so I think that's where now we're starting to see people now expect that by default. They want experience in addition to a working system.
That reminds me of something that I saw you say in an interview to somebody else, was that you'd been a long time user of kind of command line for development, and you switched to IDEs. and you go, oh yeah, okay, I see why now. And again, that's about raising that level of abstraction and making life easier, so we can do the more creative, interesting parts at some level.
I mean, for me, the IDE was about experience. I felt, I had decent tools that, did a decent job helping me kind of streamline a few things. But man, like that experience of like, as I'm working with a REST API that I'm not familiar with, I call curl and I get back that JSON response, and I just paste it in a comment in the code so I can understand, like, I'm going to write a type for this thing. And then the experience is like, hey, would you like me to generate a type for you based on this data structure? And I'm like, wow, like that, maybe there is definitely an abstraction there, but to me, that's when they cross the line into experience. Yeah. They know that, hey, a developer tends to do this. Wouldn't it be nice if we just paid attention to the buffer? And when we saw that, let's just make a prompt and let's just generate the code for them. Oh my goodness, that feels like the next level of this industry.
Yes, and I think there are a few steps further from my point of view in terms of continuous delivery. I don't think any of the continuous delivery tools are mature enough yet, but I think there's a way to go in abstracting some of those ideas further. But that's my hobby horse. Let's stick on some of yours. That going back to that idea of kind of being able to maintain our ability to make change, even when other people, disconnected people who you can't force change on, are using your software. That seems, I'm trying to figure out how to ask you this question without putting words into your mouth. One of my strategies for doing that kind of thing is one, using ideas like domain-driven design, modeling the problem in a way where I'm going to try and create a simulation of the problem. I would read some of the design choices that you and your team made in Kubernetes, as far as I could see it, as showing some hallmarks of that, modeling what it is that you're trying to build. And the other one is, particularly when building service style systems like something like Kubernetes, trying to make sure that I always do that in the context of some other real work, some real world use, so that I can be, rather than some ivory tower kind of thing. Could you just talk about those sorts of thoughts on how you apply, your design thinking, your experience, to be able to, steer things so that you get to those nice, clear, unchangeable interfaces?
Well, so in Kubernetes, they're all changeable. And the ones we can't build or shouldn't build, we let people just build it themselves. So there's one element of, let's say you're building an API to deploy applications. There are parts of the thing below your API you don't control, like POSIX semantics. We didn't choose the POSIX way of describing permissions. In 2022, no one would probably do that, right? We probably wouldn't use some hex system to describe permissions. We would probably do something more clear based on people's understanding of RBAC and the granularity needed there. But we don't get to make that choice. That's a 30-year-old, 40-year-old decision. And so our API now has to accommodate the thing that people are trying to do, right? So I want to deploy a Kubernetes container, or a container that needs to be managed by Kubernetes, but that may be the new part. But I now have to go back in my API and allow you to mount a file volume using the same semantics that POSIX holds. So if you look at the API, you can kind of see the new and the old world represented in one. And so what we decided to do was we took a declarative approach. We made sure there was no if statements or for loops in this front-facing API. And then we also did something I think that was really clever, which was we have a very explicit freeform status area. And that status area allows us to leave the spec alone. So the Kubernetes resource model, it attempts to implement promise theory. For those that are unaware of promise theory, it's this idea that the system may or may not be able to do the thing that you're asking. And so our API accommodates for that. So we don't assume a synchronous world where you're going to call the API and you're going to get an immediate response. Kubernetes design is saying you may never get a response. And so the part that you declare, the status field is where we use to update how far we are in keeping that promise. Is the container running or not? That is not found in the top part of the spec. So that gives us a lot of flexibility on changing the status, because that's up to the various low-level components that control that object. So we're less rigid in a status object than we are in the spec object. I want this container, but the states of that container can evolve with the system without us necessarily breaking compatibility at all the layers. But if you're a UI designer, you may say, wow, this new status type may not match the color palette that I use to represent the other three statuses, right? Like there's a fourth status here. Should I use purple for that? So that can be challenging. So we try to give ourselves a little leeway in that specification. But I think what Kubernetes has tried to do well was just realize there's a real world we don't control, but we want a similar feel. And when we can't do that, I think that's when we decide maybe we shouldn't tackle that. Maybe we should do this as a CRD, a custom resource definition. Let the world experiment with that before we decide should it be in the standard library or should we evolve one of the standard APIs. One good example is the ingress object. This is the thing that provides a facade to load balancers. Now, here's the problem. As you know, there's like 20, 30 different types of load balancers. Nginx, the cloud provider native ones, Envoy. There is no way we're going to create a base type that can accommodate all the features and nuances that each of those load balancers do. And so we decided to find that, 60% sweet spot of connecting containers behind a load balancer and sending traffic to them. Hey, that's enough. We can do that. Yeah. But eventually realized that people started creating annotations, which is this free-form field of key value pairs in order to influence the object that was under management. So now people are just breaking our abstraction, right? Then it just became another place, a bucket of values. And, right, you see this in programming a lot. You just got this big bag of values that it depends on the implementation, what's going to happen. And that's hard to test. It's hard to reason about. And honestly, there are no promises being kept because those are not versioned as part of the normal API. And some people started to version the annotations, right? You have a namespace that is like version, and then that gets weird. And then you have a sub kind of API going on here. And then when that pressure got too much, we decided to do Ingress V2 that took a lot of the learnings from what we've saw over the years. And of course, the spec changed. And we also realized that, maybe it's okay if there's an Nginx type, a concrete type that actually represents what Nginx can do for those that can't get by with our abstraction. Maybe they just want a bit more automation behind a clear API.
Yeah. So there's that pragmatic choice of the trying to find the generic abstractions where you can, and the concrete types where you can't. I suppose.
100%.
Yeah. Let's move on a little bit. You said that you haven't been doing any work on Kubernetes for a while, so I've kind of bored you to death by talking about your history. So let's talk about the cloud more generally. You are firmly in the cloud space in terms of promoting and helping its adoption. I think you said earlier that you've been looking a lot at serverless things. I must confess, I kind of leapfrogged the kind of Kubernetes style systems, and mostly these days, if I'm writing systems, I'm in the cloud. I'm probably writing. I either did stuff bare metal on my own, or I do serverless things when I'm doing small, simple things. Is where I got to. So I'm sorry if some of my questions were a bit on the beginner level, but I'm interested in serverless from the point of view of design and architecture once again, I suppose, in the sense that it seems to me that it changes the economics of design, and that should make us think about different ways of designing systems to be natural in a serverless world. Would you agree with that statement? I guess as a starting point.
So that's the thing. I disagree vehemently with that statement because I
Okay.
think when that came out, it was like this function-oriented, event-driven programming model. I remember writing Haskell for the first time. The way Haskell wants you to think about the world forces you to write code in a certain way. And that's okay. We need different type of constraints because sometimes that's what the system underneath it needs. That's fine. So when I saw serverless for the first time, and you go and you write your function and you realize it's not a server at all, it's a client, and there's this programming environment around you. So now the next step is to understand that programming environment. What can you do? Well, it turns out in Lambda, which is not a problem, but things tend to get initiated through their event model, right? Like whether you're getting a change notification because the database role has changed in DynamoDB, or someone has uploaded something in S3, and then an event fires off that tends to have a schema, and then you can take that and then you can respond. And so look, we've been building event-driven systems for a long time. So when I look at Lambda, Lambda is this very opinionated architecture of dealing with that, which allows Amazon to create a very clean API for just handling events from this set of types that they support. All right, cool. But that's not all software in the world. All software in the world, I guess you could try your best to force it down that architecture type if you really wanted to. And some people get excited about rebuilding things using the new architecture. And so I saw that and said, you know what? Okay, I can see how you can build some apps that way. But the truth is, people forget Amazon doesn't have one compute platform. They also have bare metal machines and VMs and container management. So you have to look at the whole. Their whole stack means it's just one element of computing. They never said that this is the future end all be all. And so in Google, we definitely have a functions platform very similar to Lambda. But when we started work on Cloud Run, we made some decisions. Is the function the right abstraction? We thought for Cloud Run, the answer is no. That is not the right abstraction. It's an abstraction, but it's not the right one. We felt that the container image, meaning you, the developer, know what language you want to use, you know what libraries you want to use, you should use that. The abstraction is the kernel. The kernel says you can make system calls to process data and do computation the way you see fit. We're not going to spend a bunch of time telling you which programming language now or in the future you can use for the system. We have a decent abstraction, the container image. Now, once we have this container image, now we can go focus on what makes computing hard. So one aspect of serverless is cost management, right? I only want to pay for this thing while it's doing something useful. And the early implementation of that, which I think was more of an implementation detail than a best practice, scaling to zero is not necessarily a best practice. It can actually be the wrong thing to do for the low-level operating system. But it's the only mechanism we had in the beginning to have a contract with you, the developer, right? Like, look, if you don't want to pay for this, then I'm not going to run it because I only have so much CPU and memory to go around. It's a scarce resource. So scale to zero it is. But now we start to understand how much of an implication that is to the underlying infrastructure. It turns out different programming languages need to actually bootstrap. Forget all the abstractions you've learned about. It turns out if you want to use something like Spring, then guess what? You have to pay for all of that serialization up and down. And so that cold start becomes right in your face. It's a leaky abstraction. Cold start said, oh, all of that stuff we tried to hide, it is now front and center. What do you want to do about it? In the Lambda world, even though we've made great strides around concurrency, the Go programming language tends to hide the complexity of concurrency behind libraries, tools like Python and Ruby, not necessarily. So when you have a programming model where the concurrency model matches the runtime, then you're fine. But what happens when that is no longer true, right? You don't want to treat Golang like Node.js. Everything isn't in an event loop. And that's another constraint that things like functions put on people. And so if you're writing Golang, you were doing all of this weird stuff to avoid creating too many Go routines because they would effectively be doing nothing. You'll be getting no benefit. So we decided that concurrency should be available by default in Cloud Run. And if you really want to go back to the other model, just set concurrency to 1. And then you're back to where you are. And we also made scaling to 0 optional. So you can now run for a long time. Long story short, my belief, and I think the team agrees, and we've implemented most of this, We want Cloud Run to do everything a bare metal or VM machine could do, including attach data volumes, attaching the GPU if you need it, but then have the operational characteristics of a serverless stack, scale to 0, scale up from 0 to 1 really fast, and then give you some type of an experience in terms of traffic management, traffic splitting, all without Kubernetes. You don't need to learn all these low-level things. You don't need to manage a Linux server. You don't have to log into it. And so we think the best of both worlds would be you write logical applications in the way you see fit. You pick your protocol, and then you let us run that application, and you tell us all the attributes around how long should it run, should it live migrate, should we tear down to 0 to save money. That's an expression of configuration. So I think Cloud Run really represents the best of both worlds. You get the flexibility of articulating complex application scenarios, and then we hide the underlying infrastructure, but you can run it in a serverless format if that's how you choose.
That's really interesting, and I'm trying to figure out where to go next, because there's part of me that wants to argue with you about some of that, and I'm not quite sure that's the best use of the time to invite an expert and then disagree with them. So, but
no, I mean, I think so. One thing I would welcome is one thing that we did well in the Kubernetes community. We took all the disagreements as a feedback loop,
yeah,
right? Because when we were doing this thing, I remember there were a lot of people very vocal. It's like, if you give people choice, they might use them. And then we will lose all the beauties of a constrained system. And then we'd say, well, what constraints make sense to you? And they would list them. And they would ask another person, what constraints make sense to you? And they would list them. And then we would stand back. And it turns out, if you get enough people to list the constraints that they need to be productive, remember, we're a cloud provider. We serve all.
Yeah.
And so these underlying stacks, we tend to try to make the right balance so that we're not unnecessarily introducing constraints that you can't necessarily do by a configuration.
Sure. It's an interesting idea. And presumably that means for systems that are hard to start up and so on, you're kind of keeping some kind of cache of processes that you can bring into use if they're needing it and so on, in order to give that illusion of startup from 0 and you're carrying the cost of that.
Well, no, we just let you be explicit. We just let you say,
okay,
I want 3 of these and only 3. That's all I'm willing to pay for. We've architected our system for 3. Okay. Or you could say, I want 3 with this much memory and CPU, but I'm willing to auto scale from 3 to 20 if need be. Right? That beautiful, because as a developer, when you're interacting with the real world, ideally you're doing something like performance testing, capacity planning. And if that capacity planning tells you that you should have 3 always between 8 a.m. and 9 p.m. and then auto scale thereafter, shouldn't you be able to articulate that to the system? Now, that's what we're trying to do today. Now, tomorrow, we can use the traffic patterns to make a better autoscaler where you won't have to do that anymore. You can just say, let the system figure it out. And then maybe the system will observe your traffic patterns and calculate that same set of configuration for you, put it in place. But the one thing I've learned about autoscalers is that sometimes they're not really designed for unpredictable things. Like or predictable things. I know on Friday, my company's about to launch a massive campaign. There has been no data to train the autoscaler that will be true. Now I need a manual override. And I want to say, give me 20 of these things before 8 o'clock and autoscale to 100 today only.
But one of the I suppose one of the heresies that I've held for a very, very, very long time, I got interested in distributed computing bloody decades ago. I'm very old, and was I was doing stuff with distributed computing in different forms for a long time, and there's always been this kind of conversation, it seems to me, about stateful or stateless, and obviously, that makes a big difference. And I think this is a difference that you were alluding to the complexity of the systems. As soon, if you can have pieces that are stateless, it's easy to be able to, scale them up, duplicate them, and so on. And as soon as you have state somewhere, it gets more complicated. Part of my background towards the end of my career, when I was building real systems rather than talking about building systems, was building high performance financial systems. And you couldn't afford the cost of storing that state in other places. So we did smart things with clustering and treating in-memory state of the system as the truth. And that puts limits on how you can deal with concurrency, or how you should deal with concurrency, and all of those kinds of issues. And so, it's a corner case, but it led us into some interesting routes in terms of design. And one of the things that we came to, I was involved in a team where we built what is probably certainly one of, if not the highest performance financial exchange in the world. And we came with an interesting architecture, and a lot of what you've described we built it for ourselves. We did the stuff that I would agree most people shouldn't do this, because it's bloody hard work, and it puts you at risk of missing loads of things, and you have to do loads more than you want to just get the behaviors that you need. But we did that to get the levels of performance that we wanted. But one of the routes that we took was, and I'm not saying this is right for everybody, but I think it was to me, it's a more distributed model. And I'm bringing it up because you said something that triggered me to say it, which is that distributed computing is not just about, these stateful servers all over the place. It's not just about serverless, just function as a service or what. It's more diverse than that. It's more heterogeneous than that. And so you want compute where you need the compute. Sometimes you want compute, at the client. You don't want to be offloading that to the server. You want it to be there, here and live with, where I'm interacting. And other times you want it centralized and elsewhere. And that's a more complicated problem than just the technologies. That's about thinking quite deeply about communication strategies and so on. So people like you can help us to abstract some of that and build tools that make it easier to make those choices. But one of the things one of the things that I see in lots of my clients' software is people don't think in those sorts of terms. So I'm interested in how you think we should surface those sorts of choices.
So it's all layers, right? And so I'm an advisor to Vercel, the company behind Next.js. Okay. And we did a fireside chat with the founder, Guillermo, at the Vercel conference. And since I started advising them a couple of years ago, number one, I asked, why would you want someone who spends so much time in the back end to be an advisor to a front end, dev-focused company? And, and we had this conversation, and, cloud comes from this thought of the data centers, the computer, right? There's this common theme around distributed systems. You try to take a bunch of small things and make them look like one thing. And then there's consensus protocols in between. And one of the things that I was coming up with is like, if you treat the web as a computer, and then what you start to do is expand in many ways that memory model, like the browser becomes like L1 cache. It's the fastest thing you can do.
Yeah.
And CDNs allow us to serve and load our programs into that place, but you only have so much functionality you can do there, right? So it's only so big, these client devices. Yeah. And also there's some data that doesn't belong there because it can be dangerous, right? I'm not going to load all of your data in one shot to the browser. So then we look one tier back. And so we have this edge, like the CDN itself, or the first place where that next hop goes, which typically for some companies is no longer the backend origin server, right? It's usually something like Cloudflare, Fastly, or Alchemy. And those things are starting to look like L2 caches where you can put some logic there as well. And so and then there's some things that are just too heavy, like the thing that needs to really connect to the database, maybe to a Redis cache. Like that's going to be a lot more stuff you need to do that is not appropriate to have running side by side next to network functions that you find in a CDN. And so if you look at the Next.js stack, by convention, depending on where you put your code, it will choose part of that code to run in something like Cloudflare Workers. Part of that code will run in something like AWS Lambda, or you can probably just point it to a container like you've always done with some direct URL. And so they treat the web as a computer. And the thing we talked about a lot in that fireside chat, it went on for an hour and a half. We talked about data. Data is the thing that helps people decide what to do. So when I think about systems, and I try to simplify things, maybe to the point where I've gone too far, but no binary that I've ever seen, not even the database binary, like the Postgres binary doesn't store data, not itself, right? That thing is a stateless thing that happens to rely on state being in a well-known location. Thanks to POSIX, for most people, that's a local file system on a server. And even on the server, that file system could be backed by an SSD. It could be an NFS volume. But I think the nature of POSIX has forced this concept of write, close, open, and it doesn't account for the messy truth of the network. You may do a write call and may not necessarily get the response you want. You're going to get network-related errors that have nothing to do with inodes or the capacity of a local disk. And so I think that's where a lot of us struggle in the systems we build. If you're targeting a POSIX interface, and in some ways it ties you to the operating system semantics. But I think what we see in most distributed systems, that especially the ones where Kubernetes gets its origin, Kubernetes comes from a lot of the thinking at Google that file data access should be very explicit. If you have a blob of data, let's not think in terms of POSIX. Maybe that should be an object store, and it should have versions and metadata, and just acknowledge that the network sits in between. If you want a SQL abstraction, then use a database somewhere over there. Mm-hmm. And then what that does is, I would even say most of these web apps are somewhat semi-stateful because they usually cache certain amounts of data, sticky sessions, cookies, right? They tend to have something to try to speed up the next request. Yeah. But what we try to do, especially in highly available systems, we know that we can't keep that session only in that one app, because if it crashed, then the user would have to start over. So I think this all comes down to, which I think Kubernetes assumes, we're going to live in a world where POSIX cannot be the dominant way of thinking about storage. And if you do that, then yes, you can treat the web as a computer and think about all the layers from the browser, SQLite running in WASM, down to something running on Oracle on bare metal.
I like that analogy. I spent too much time thinking about the internal workings of CPUs, so that analogy works really well for me. it's a nice one, thank you. There's another topic that I know that you've spoken about publicly. I don't know whether it's one of your current interests or focuses particularly, but about kind of the security and provenance of our software. Tell us a little bit about that, about SLSA and those sorts of ideas, the software supply chain.
Yeah, so my whole career, like you, security is there. It's always there, right? There's either someone that's going to educate you about how secure your system is by borrowing your data, right? That's a polite way to take that. And right, we don't write software with that intention in mind. We want the software to work only as intended. And I know you come from a strong testing background, and a lot of that is trying to do that, right? Let's make sure the software only works as intended. And I think security also has its roots in that logic. We only want the right traffic going to this application, and we only want the right responses coming back.
Yeah.
Unfortunately, as you know, right, computers are messy. They're undeterministic things that happen that can be exploited. And so I think there's a couple of options here, right? There's a lot of low-level things about how to prevent those things. And some people like to then predicate on patch management and vulnerability scanning. But the thing I wanted to do by understanding the SALSA framework that you alluded to, we have to take a step back. We're not going to necessarily always get it right where we write 100% correct software all the time because of that relationship between software and hardware. What's that? I said this thing, I'm pretty sure someone said it before. What does the saying go? The same person can't cross the same river twice, right? Because the river and the man will be different. And I think software is very similar. You can't run the same program twice. The time and the machine will be different. And so given that, we need to understand what's in the software. And for a long time as our industry, people don't really think about dependencies very deeply, right? Some people are just pulling software from random places on the internet. They have no idea who wrote that code, whether they've introduced a malicious bug on purpose, or maybe they stopped thinking about performance out of the sake of convenience, and it's going to have an impact on my app. A lot of people aren't tracking that as well as they should. So as a start, one thing that I think is important is, as a developer, an artist typically signs their painting. So you know it's authentic and it's from them.
Yeah.
But we don't have a habit of signing our software. We don't even know who wrote it, right? And so I think given that Git has the mechanism to help people start signing their software, so we can start tracing back what section of code was written by who, because maybe there's a person that has a bad reputation that we would like to not pull software in from. The next step from that is, if you're baking a cake, then you need to know what the ingredients are, because if someone in your audience or at the party is allergic to a certain thing, we may not want to bake that into our cake. And I think the same is true of software. We should be cognizant of what we're putting in that software so it runs appropriately. And so I think that software bill of materials, like raising our security discipline on the software engineering side to be very clear about what's inside of that final binary that we plan to release and ship to other people. And I think the also part about signing these artifacts, right? This idea that I should be able to take the same source code and produce the same binary. That should be possible. But most build tools, that is not, because they usually append temporary directories inside of the things that get included in the binary. They usually have timestamps, which makes this impossible. And so given that, then you can't get reproducible software. And so imagine testing something and the thing you're testing cannot be reproduced. I think that would be a problem, right? We need to have some base level things that are true. Like I remember getting into testing for the first time and finding out how important it was to have consistent test data.
Yeah.
That could help us understand, like, this is my base. And as long as this test data results in the same output, then I know the software gives me freedom to change the software because I know the inputs and outputs will be the same. But what happens when you can't even produce the same binary and you start, like, what's going on here? So getting to reproducible binaries, software bill of materials feed into that. So now what we get now is, maybe there's one more thing here. I need to understand the thing that is producing this SBOM or this particular hash of this binary. And the new famous paper, Do You Trust Your Compiler, right? Like, what is the thing doing underneath you? Can you trust it? And it turns out there has been lots of backdoors that have been injected. I think there was one famous one where the code coverage software was injecting things into the final binary. That's dangerous, right? And so I think what we're now starting to do is we need to understand the build environment, because the compiler and all of these additional tools contribute to the final output. And so now what we talk about is build provenance. Who built it? When did you build it? What were the inputs? What came out of it? And that gives me a chance to have a separate build system asserting the same things, and they both better put out the same binary.
There's a deep crossover here with my territory, continuous delivery, in terms of being able to, the approach to trying to get asymptotically closer and closer and closer to that determinism. And so one of the things that I've talked about in the past in the context of continuous delivery is that all of the build infrastructure is a dependency of your system. All of the the deployment pipeline is a dependency of your system. You should be able to, in an ideal world, you'd be able to go back to a version of your system that was running in production 2 years ago and recreate it from version controlled information precisely and get the same stream of bytes at the end. That's what you should be able to do. And controlling the infrastructure, the environments, and the tooling to get to that point are part of that. So, sorry, that's just my hobby horse.
Oh, you're exactly right.
No, go ahead.
No, I think you're exactly right, because if you think about a restaurant that has a delivery service, like a pizza shop, right? You can call and deliver a pizza. And the reason why it works is because you tend to get the same pizza. It tastes the same, right? Whether or today or next week. There's a quality control element that people are ordering from here because they expect it to taste a certain way. And if we can't make reproducible pizzas, then people may not want to order from us because they don't know what they're going to get. So there's something about a reliable artifact if you want to be able to scale your delivery model.
I can give you a real world concrete example of a failure caused by that. I was involved in a team where we built a point of sale system for one of the big retailers in the UK. And at some point, we got some weird difference in the system in two different test environments. It was behaving differently in these different places. And we couldn't figure it out because we'd done quite a good job of infrastructure as code and managing this and, nailing it all down. We'd version controlled all the things. We couldn't work it out. And we did all sorts of things to try and figure it out. To cut a long story short, we ended up doing a complete system audit of everything deployed on the two different instances. And we brought it down to the version of the checksum of a library in the IBM version of Java, which was different on one version and another. We weren't even aware that we were using that library, but it changed the behavior of our software in a way that we could notice in our tests. And so you need to do that sort of stuff. I'm with you on this. I think this is important. One of the things that seems really important to me, and I assume this is something that people like you, if not you, are looking at, is to improve the tooling to make this easier for people to be able to do that thing of initially just the bootstrapping exercise, but at least let's be able to determine the provenance. Let's be able to say, yeah, it was definitely Dave Farley that screwed this up. You should be able to do that.
Also, this is the gift that Docker brought to the whole industry. If people would, I think, again, remember, so everything we just talked about is very complex.
Yes.
We've just been ignoring it for decades.
Yeah.
And so when you look at what Docker does by default, it gives you almost the ability to create a clean room environment.
Yes.
When I used to build RPMs in Red Hat, we used to use a tool called mock that would create a true root, and then just start over clean so that we had a chance at getting a reproducible RPM out of the system. What Docker does that for all the languages, right? And so now that you have this kind of thing that just says, here's my Docker file, I'm going to start from a base that is known, and then I'm going to add my dependencies, and depending on your build tools, like in Golang, we try to make this a little easier, I can actually do everything we just talked about and then store the image in a registry that allows me to attach the SBOM, to attach all of these build providence things. And so, but this just moves the world forward. So again, if you're a new developer and you start learning how to use things like Docker, you're like 95% of the way there to building reproducible software along with all the things that you find in that salsa framework.
Fantastic. I'm looking at the time. I think we're coming to the end of our time, and I'm conscious that you're a busy man, and I thank you again for the time that you've given us here today and the value of your experience. It's been a fantastic conversation. I found it really interesting. I could carry on talking to you for a long time because there's stuff that I want to argue with you about. But I think that we're in a huge amount of agreement on a lot of stuff. Fascinating.
You know what? I would be interested, and you can cut this however you want. What would be those things? Because I find that I grow in my own understanding when people do like pushback. So if there's something maybe in this conversation or maybe in your notes that say, you know what, I really want to challenge this one thing, let's do it. You decide if you want to keep it or not. I do have a bit more time. So unless you have a hard stop,
cool.
Only for a few minutes.
So this is one of those problems that I can see the challenges for. But one of the things that you said, you're Google and you're running the software for the world, so you can't be too opinionated about what it is. I buy that. I understand that. But there's also this thing of raising that level of abstraction, step by step. It's how we make progress. It's what Kubernetes did. It's what operating systems did. When I first started, the generation of operating systems that I started with, if you wanted to print something, you had to write in assembler the code to talk to your specific printer. The idea of printer drivers was a radical concept and a cool one when it came along. So that incremental stepwise improvement in abstraction seems important. And one of the nicest big system that I've ever seen was the exchange that we built when we built the exchange at LMAX. And it had lots of nice properties, and some of them were add complicators and so on. But one of the things that it strikes me is, and I'm always on the fence about this, is that there seem to be different groups of programmers. And I feel bad saying this, but it feels to me that there are the programmers that are assembling the high-level pieces, and there are people like you that are building the plumbing, the technical things that facilitate that assembly of the high-level pieces. And I wonder whether there are better ways of abstracting the problem so that you can do more of that job of the plumbing by just making the programming model a little bit more abstractive. The key idea that I'm talking about here from my experience is the difference between synchronous and asynchronous systems. I think that asynchronous systems are much closer to the truth of the universe and much closer to the truth of software fundamentally, and that synchrony is kind of this artificial, slightly weird thing when you stop and pay attention to it, way of interacting with systems. And if you start, my belief is that if you start to use asynchrony as adopt asynchrony as kind of an overarching approach, it gives you the ability to put much more of the accidental complexity of the system away from the core of the system that's actually doing interesting things. And that's it. We built our exchange like that. Our exchange, we essentially built some kind of a custom service mesh, which was ridiculously, blisteringly high performance and did clustering and fault tolerance and security, and a lot of the services that you talked about we had in that. But the actual services themselves were single-threaded and almost like pure domain-driven design domain models. They were stateful where we needed them to be stateful, and not in other circumstances. And it reminded me of going back to programming when I was young and just learning, where everything looked simple. It was a beautiful way of building systems, even these complicated distributed ultra high performance systems. One of the ideas that I came across, and one of the things I was wondering about whether one of the routes that we would take when we were talking about the serverless thing, is I've heard people talking about stateful serverless. And I've wondered about whether that's a route to something simple. The other model that what I'm talking about is related to. So we did a thing called the Reactive Manifesto off the back of the exchange, and talking about building really reactive systems, event-based systems, but plus. One of the stateful serverless seems to me to be an opportunity for infrastructure providers like Google and others to be able to raise that bar a little further in terms of provide a programming model that allows you to focus primarily on the problem domain, and that you do all of the work of, clustering and concurrency and managing those things separately and elsewhere, and scalability. And I think that's possible, and I was just wondering whether that was a route that our conversation could go in. And the other thing, you asked me to mention the things that I would challenge you on a little bit, is I think we can take determinism further. So the reason that there are, as far as I can see, there's only 2, maybe 1.5 reasons why our systems aren't deterministic. So one of them is concurrency. That's the biggie. As soon as our system's concurrent, they're no longer deterministic. So we can manage concurrency at the margins of our system in the appropriate places and limit its impact. And the other one is, where we consciously inject some random feature, some randomness into our algorithms. And I think that architecting to try and limit the boundaries of the non-determinism of our systems is a very healthy way to get to more testable, higher quality systems. So those are the things that I would be interested in kind of having a deeper conversation with you sometime.
Let's walk through some of those. Like when I learned Haskell for the first time, their philosophy around functional-based programming had a lot of those tenets. And there's always one thing. You could do that in your own isolated view of the world, on your own one box with a single threaded. You can do that. But then we have this thing called the network, which is all of those non-deterministic things. That's the network, period. That's how networks work. There will be collisions. There will be retries. Things will come and go. You can't predict that. And so no matter what we do at the app level, the moment we have to interact with something elsewhere, then it all comes back. You can pick whatever model for the app. You still have to deal with this other world. That's it. And so unless someone figures that out, that's just the nature of the world. It is. So it's like, where do you put it? Right? We know the network is not going to be reliable 100% of the time. That is a guarantee. And so now we have things like load balancers where we try to isolate this. They do all the retry logic. They try to smooth over these rough edges so we can keep that logic out of the app. So the app just assumes a simple world, and we put the reality in the load balancer. Maybe you put the reality in the VPC. So cloud providers do a lot of this at the low levels. A lot of people just feel that, oh, I'm just calling this IP, but a lot of this is actually happening for the messy world of networking in that VPC to make sure your packets actually make it to the other side and come back. So I think a lot of these things are already hidden from a lot of people. They're already there. I mean, if you think about managed databases, in many ways, that's what they're doing. Like Cloud Spanner, which is a multi-region SQL database with strong consistency. You just, as a developer, you say insert into, you have no idea that that data is being replicated, being sharded for performance. It's doing all of this hard stuff, dealing with time and consistency. And we have to have trade-offs, right? There's a such thing as speed of light. And so systems like Spanner say, look, the upper bound of consistency is 7 milliseconds. So as a developer, you know, if you just wait 7 milliseconds, things will have a total ordering that you can count on. And therefore, you can just focus on inserting and retrieving data. And the libraries tend to work out this 7 millisecond thing on your behalf. So I think we have a lot of these components, but I think the thing that makes a lot of this stuff really complicated is that, and I think we want this as humans, as much as we want this standardization, as much as we want to take away some of this complexity, the beautiful thing about our world, like I'm into hip hop, it's a great genre of music, but it comes from a lot of people who may not have had the full discipline of what music is. Maybe they can't even read music, but when you hear it, you're like, wow, if they would have followed the rules, it would never have existed. And I think a lot of the people who we've invited to build things, they're going to start with the canvas we give them. Some people are going to start with Next.js. Some people are going to start with Python. And given those canvases, they're just going to create things. And I think it's on us as builder of the frameworks, builder of the libraries, to take all the stuff that you've talked about. I mean, the reason why I love Go is because it's like the first programming language that actually took the best of concurrency and let me keep the simplicity of synchrony, right? I can just say, call this, call that. And under the hood, Go was working out the true world of things can happen in parallel, things can happen in a concurrent manner. But for me, in my code base, I wasn't articulating all of those things. I was just taking traffic and passing it to the right handler, and Go did all the right things on the back end. And I think we can do that. And I think it's going to come into the forms of libraries and frameworks. Cloud providers are also trying to do this at the different protocols. So I do like this idea that if we can come up with really good protocols that allow you to do the thing you want to do, and the implementation of those protocols may deal with the real world complexity of all the things we just talked about. And for the large part, I think that's what cloud is. And last thing I'll say here is the thing that makes cloud hard, because you remember when Google Cloud came out, we only had one service, App Engine. And it was a PaaS, and we had one cache, we had one data store. And the idea is that we've abstracted all of this hard global Google infrastructure. Just write App Engine apps, and you don't have to think about any of this stuff. And the world, like the people who pay money for stuff, they're like, nope, we want protocols like Linux. We want protocols like SQL. We want all the things that we're used to, because we didn't just start building software today. We have existing software that we would like to move in this world. So now as a cloud provider, we have to approach, we've chosen to approach this with the whole spectrum in mind.
Sure. One more challenge to that. I buy what you're saying entirely, but just one more challenge to that, which is that it seemed to me that the serverless thing was an opportunity. The serverless thing. We talked about this in a slightly different way. When I said about it changing the economics of software development, what I really meant was that we change from cost per byte to cost per CPU cycle. That's fundamentally what seems to me that serverless does, and that changes the way that we should think about data, how we store it. Maybe normalization is a stupid idea because CPU is more expensive than storage. Those sorts of ideas. So that gives us an opportunity to just think a little bit differently and have a slightly different model for distributed computing. And the next step for me that would make sense to that is to give the illusion of this kind of stateful serverless model where effectively you're building actors. And then that gives you an opportunity to do a whole bunch of smarter things in the background, configurable, not just the same shape for everybody, but it allows people to focus more on the problem that they're solving and less on the tech that they're using to solve it with.
But I think the key here is that experience dominates all of that. GitHub is a monolith built in Ruby on Rails that ignores all of that, right? And just says, but you have GitHub and it's number one from an experience standpoint.
Yes.
And I think the biggest challenge we've seen in our industry is there are people who build really good new patterns. The biggest challenge is adoption.
Yes.
Adoption. I think this is why great engineers have the ability to communicate and grow adoption. And I've seen a lot of engineers I've met that are super frustrated. We've built the best memory model. We have everything. We've solved all the world's problems. But did you talk to anybody? Did you inspire anyone? Did you show them what they could build? Did you go into the weird parts of the ecosystem that are coming from a different era? They're coming from COBOL. They're coming from existing systems. They don't have the people to rewrite this current app while adopting this new model. Did you do all of those things? And if the answer is no, then thou shalt not have adoption. And you will watch the world go in a different direction, even though you have the signposts pointing in the right direction. And I think that's the struggle that engineering. So the thing I like to think of is in engineering, we tend to favor people who can keep going lower, right? You write code. We like people who understand how the compiler works. We like people who understand how assembly works, and then how system calls work, and then how the hardware passes electricity around to make it happen. But what about the other direction, right? And this is where we hit the surface of what should the API be, right? And then above that is how is it used? Above that is who's using it? We don't typically go that high. Most people stop at the API. So the higher you go up, you hit the human. And most people don't like the human level because humans are subjective. Humans are opinionated. You can be right at the wrong time. Ask Sun Microsystems. They were so early on so many things. They were right at the wrong time, multiple times. And so I think that's where when we depart from the computer and we get to the human layer, a lot of this stuff tends to blow up. And I think that's been the hardest part about any of the things we talked about is as engineers, we're realizing social is a part of engineering.
Absolutely.
And if we want to see great adoption, I think that's the other side of the coin.
If there's a place to stop, that's it. That's absolutely 100% right. And I think we are in complete agreement on that. It's been an absolute pleasure talking to you. I've had a lot of fun. Thank you very much.
Thanks for having me. I really enjoyed this.
Cool, thank you. And for watchers, please do hit subscribe and like if you've enjoyed it. Put some comments, argue with me and Kelsey. Tell us that Kelsey's right and I'm just talking rubbish, which is usually the case. It's been a lot of fun. Thank you very much, Kelsey, and thank you for agreeing to do this. Bye-bye.